This lecture is about eggs. Eggs are very versatile. We cook and eat them plain. This can be in the shell as hard-boiled eggs or soft-boiled eggs. We also can poach them, can fry them, scramble them, and so forth. Eggs are also commonly used as ingredients in a variety of different foods, and they're used as ingredients because of their ability to form foams, because of their ability to emulsify, and because of their ability to coagulate or form gels when they're heated. And we have observed all of these already in this class. We've talked about foam formation, we've talked about emulsifiers, and also in the custard lab we saw how eggs can coagulate and convert a fluid substance to a solid substance. I'm going to start first by looking at the structure of an egg, and we'll start with the outside of the egg, which is sort of the shell of the egg. The shell is hard because of calcium carbonate. It's also porous. There are very tiny holes in it, and that allows gases to exchange in and out of the egg. This is important because the egg is going to house a developing chicken embryo. That chicken embryo is going to need to be able to breathe, so to speak, and so gases have to be able to go in and out of that egg. Immediately inside the shell of the egg, we have two membranes. One of those clings to the shell, and the other one clings to the contents. And after an egg is laid, it cools, and the inside shrinks a bit when it cools, but of course the shell does not shrink, and this creates an air cell or an airspace in the egg. Moving in from these membranes, we get to the white, and there is both thick and thin white. We find thin white up next to the membrane by the shell, and we find thin white again very close to the yolk, around the membrane surrounding the yolk. Otherwise, most of the white in the egg is thick white. Moving on in, there's a membrane that surrounds the yolk. This is the Vitellin membrane, and the Vitellin membrane towards the ends of the yolk twists and forms this sort of ropey structure, which is called the chalaza, and that ropey structure attaches the yolk to the membranes by the shell. This permits the yolk to rotate but still stay in the center of the egg. And the very center of an egg is, of course, the yolk. So now we'll look separately at the white and the yolk of the egg, and so we'll start by looking at the egg white. The egg white seems fairly simple. It's 88% water, which is mainly what it is, and 11% protein, and there's only 1% of like everything else. So the main constituents are water and the protein. Since the main component of white other than water is protein, we'll look at the proteins and their functions in egg whites. The major protein in egg white is ovalbumin. It's more than half the protein that occurs in egg white. It is denatured by heat, and when it's denatured, it forms a rigid gel structure. And so it's the protein that's important for the coagulation of eggs on heating. And also it's going to be the protein that's responsible for the gelling of other foods to which eggs are added. The ovalbumin is also denatured by whipping, and so it's the major protein that's responsible for the foaming properties of egg white. So most of what we use egg whites for in terms of foaming or coagulating, we get from the ovalbumin in the egg white. Ovomucin provides the jelly-like characteristic of the raw egg whites. The thick white has more ovomucin in it than does the thin white. Now, eggs are not really designed for human food, to make souffles and custards out of. They're really designed to house developing embryos. And if you think about this, after the egg is laid, if the egg gets fertilized, it's going to be incubated at about 90 degrees Fahrenheit for about 3 weeks. And this temperature is ideal for microbial growth, and eggs are very high in nutrients. But the eggs don't spoil during this 3 weeks at 90 degrees Fahrenheit. They do not spoil because of several built-in defense mechanisms. So the first of these would go back as the shell. So the shell keeps a lot of the microorganisms out, but the shell is porous. It has sort of pinholes in it, so it can let some bacteria in, so it's not impervious to bacteria. When the egg comes out of the chicken, it's coated with a substance that's called bloom, and that substance clogs many of the pores, which is helpful for preventing microorganisms from going into the egg. Much of that bloom is washed off commercially because it makes eggs look dirty, and people don't like that on their eggs, so it's cleaned off. So bacteria can get in through the shell, and the next line of defense will be those two membranes, but bacteria can make it across those two membranes, and then the bacteria can enter the egg white. Now, the egg white contains proteins, about 4 different proteins that serve as defense mechanisms, and these are listed here. So the first of these is lysozyme. Lysozyme breaks the cell walls of certain microorganisms, killing them. Ovomucoid is a protein, and ovomucoid is a trypsin inhibitor. So trypsin is a digestive enzyme that digests proteins. So bacteria have trypsin, so they can digest the egg white protein. But this trypsin inhibitor is going to prevent the bacteria from digesting the egg white protein. So it's also a defense mechanism. The third of these is avidin. Avidin binds biotin. Biotin is a vitamin. Microorganisms need biotin to grow. And if this protein binds the biotin, then it's not available to the microorganisms. So even if they can enter into the egg, they can't grow there. And the last is conalbumin, and conalbumin is a protein that binds iron. And conalbumin is going to inhibit the growth of microorganisms that need iron to live. Now if we look at the yolk, the composition of the yolk is very, very different from the composition of the white. It's 50% water as opposed to 88% water for the white. It's 16% protein. The white was only 11% protein. And it's 32% fat, and there was really no fat in the white. So many of the proteins in the egg yolk are lipoproteins, and a lipoprotein is a protein with some lipid attached. These are responsible for the gelling of egg yolks when they're frozen. The yolk is especially known for lecithin, which is one of the phospholipids. In fact, 1/4 of the fat that is in egg yolks is phospholipids. Lecithin being probably the most frequently occurring of the phospholipids, but there are several other phospholipids that are also very functional as emulsifiers. The phospholipids are, of course, responsible for keeping that fat suspended throughout the egg yolk instead of having it separate and rising to whatever the top of the egg would be. The color of egg yolks is usually yellowish to orangish, but can take on other strange colors as well. If you have the yellow-orange color, these are due to xanthophylls. Diet is very important for determining the color of the egg yolks. Most chickens that are commercial producers of eggs are fed a diet that produces a nice orange yolk. Egg substitutes have become common over the past many years because eggs tend to be high in fat, especially the yolks are high in fat, and the yolks were also high in cholesterol, and the fat that the yolks are high in is saturated fat. Many people have been trying to avoid those in their diet, and so the food industry has responded with egg substitutes. The egg substitutes are pretty much 2 different types. The first type is shown by the egg beaters, and if we look at an ingredient label for egg beaters, it's pretty much just egg whites. And then a few vitamins added back, and it's colored with beta carotene to give an orangish color. If you can use egg beaters as an egg substitute, if you want the egg, if you're using the egg in a product to coagulate or to gel on heating, you can use the egg beaters for foam formation. The egg beaters, you have to read the label. They're less good as an emulsifier, although they do have proteins in them, and some proteins are going to be partly fat soluble, partly water soluble, and so they can be emulsifiers, but by and large the proteins in egg whites are not that good at emulsifying. sort of the vegan egg substitute, so this has no animal products in it. And this is one example of this. In their list of ingredients, they have potato starch, tapioca flour. So this is going to allow this to be used as a thickener, because we have the starch and the flour that will gelatinize and will thicken your product. Some things are in here more for stabilization. Vegetable gums, methyl cellulose is sort of a type of a vegetable gum. These also are going to provide structure both for thickening and also for foaming. You won't be able to foam a starch gel, but you can foam a solution of these vegetable gums and methyl cellulose. So this type of an egg substitute will serve to coagulate, and it will serve to foam. You have to read the ingredient list to see if it could also serve as an emulsifier. You would need to see something like lecithin added as an ingredient, and that would be the same thing going back to the egg beaters. If lecithin was added as an ingredient to here, it probably would work as an emulsifier. We talked about the ability of eggs to prevent themselves from microbial destruction, but in spite of their ability to prevent a lot of microbial destruction, they do change on age. During this time, the eggs undergo changes in quality. And the notable changes in quality are that the thick white becomes thinner. This is one of the major indexes of quality in eggs. The thicker your egg white is, or the more thick egg white you have as opposed to thin egg white, the thicker and firmer custards will be, the more resistant the egg whites will be to overbeating when they're forming a foam. And I think probably the most important thing about having a thick white is if you are making poached eggs. And when you make poached eggs, you usually have simmering water, you crack the egg, and you just drop it very gently into the simmering water. It stays together and the white begins to coagulate, containing the egg and the yolk. If you have a lot of thick white and a very fresh egg, that white hangs right around the yolk and your poached egg is somewhat round. If you have a lot of thin white, when you crack that egg and you release it into the water, the thin white just runs all through the water and you have scraggly masses of coagulating egg white, which is not nearly as attractive. Also, during aging of the eggs, the pH of the white increases. It increases from about 7.6 or so when the egg is freshly laid. A freshly laid egg already has a pH above 7. So the freshly laid egg pH is about 7.6, and that will increase to about 9 on aging or on storage. This rise in pH is due to loss of carbon dioxide. In the freshly laid egg, the carbon dioxide is pretty much in the white. It's dissolved in the white, and it's dissolved in the form of carbonic acid. And then as the egg sits over days and weeks, the carbonic acid releases carbon dioxide as a gas, and then the gas can, of course, escape through the eggshell. And as the carbonic acid releases carbon dioxide and that goes off as the gas, the pH of the egg white increases. Another change that occurs in egg quality over aging is that the egg loses water. And it's losing water because water is evaporating through the shell. As it loses water, the air pocket gets larger. Often this is partially prevented by dipping the egg in a light mineral oil or spraying the eggs with a very light coating of mineral oil. That mineral oil will then block a lot of the pores in the shells that allow gas to transfer in and out of the egg. That's done commonly commercially. If it's not done, if you're buying eggs from a local farmer that does not treat them that way, your eggs on storage will probably lose quite a bit more water than they would have had you bought commercial eggs. Now, if you're cooking eggs in the shell, so if you're making hard-boiled eggs, there are two very common problems that you will almost certainly run into if you do this very often. The first of these is the egg being hard to peel. And if you haven't experienced this, this is an egg that's hard to peel. It was cooked, it was cooled down, and now you're removing the shell. But when you remove the shell, white is attached to the shell, and as you remove the shell, you end up moving chunks of white, and this makes your egg have a surface like this, where you really want an egg with a perfectly smooth, shiny surface, something like this. So these eggs were easy to peel. These eggs were hard to peel. The hard to peel quality is associated with the pH of the egg. If the pH of the egg is much below a pH of 8.9, then the egg is going to be harder to peel. The higher the pH of the egg, and especially if it's pushing the pH of 9, is going to be easier to peel. So older eggs have higher pHs, and older eggs are easier to peel. The other issue that we often have with hard-boiled eggs is that you end up with a dark greenish color around the yolk. So that's shown here a little bit. You can see a little bit of that dark, it looks dark green. That is due to ferrous sulfide. And how you get ferrous sulfide on the surface of the egg yolk, the process for that is that the sulfur is coming from proteins in the white. So as you heat the egg, sulfur breaks off of the proteins in the white, and that sulfur migrates towards the center of the egg. It migrates towards the center of the egg because the center of the egg is cooler and therefore has a little lower pressure. So the broken off sulfur migrates towards the center of the egg. When it hits the yolk, it reacts with iron in the yolk, and you get this ferrous sulfide. You get more of this ferrous sulfide forming at higher pHs. So this is your older eggs are going to have more of this ferrous sulfate. And you get more of this ferrous sulfate forming the longer you cook it and or the higher the temperature at which you cook. The higher temperature because it breaks off more sulfur from the proteins, and the longer the cooking time because the longer the cooking time you have, the more sulfur you're going to break off on the proteins. So the typical ways to control the formation of this ferrous sulfide around your yolk are to use fresher eggs, because fresher eggs are going to have lower pHs. It's also another strategy is to cook the egg minimally, because the longer you cook it, the higher the temperature at which you cook it, the more of this ferrous sulfide you're going to get. And another strategy is once your egg is done cooking, if you put it immediately into pretty cold water, now the cold water that the egg is sitting in has a lower pressure, and the sulfur that is broken off of the egg white proteins is now going to start migrating out to the shell of the egg and beyond. And it will change its direction of migration, so it no longer is going towards the yolk. And one of the more difficult things to make is deviled eggs. If you don't know what a deviled egg is, you start with a hard-boiled egg, you cut the hard-boiled egg in half, and you scoop out the yolk, and you mix it with a bunch of other things, and then you fill it back into the empty white containers. Deviled eggs can be a problem because if you couldn't peel your eggs, these white shells are no longer very attractive. And if you can't peel your eggs, it's probably because your eggs are really fresh. So if you can peel your eggs, that's no problem. That's because your eggs are old. But if your eggs are old, a couple things are going on. Then you have more thin white, not so much thick white. And so it's much more likely that the place in the center that you will then stuff your egg yolk mixture is that's going to be off center, because without so much white, thick white, the yolk is no longer held so perfectly in the center of the egg. Also, as the egg gets older, which makes it easier to peel, you're going to develop more of the iron sulfide, and that's going to make the color of the yolk a little bit more on the greenish side as opposed to the bright yellow color. Just a couple words about egg flavor. The main flavor of eggs is actually hydrogen sulfide. If people say, oh, it smells eggy, it usually means it has some hydrogen sulfide. So hydrogen sulfide can be a horribly bad smelling thing, but at very, very low concentrations, which is the concentrations that you have coming off of egg, it is pretty much the character of egg. And of course, you're going to get more of this hydrogen sulfide released at higher pHs. The hydrogen sulfide is also the stuff that's breaking off the proteins and moving towards the yolk, which is going to cause the buildup of iron sulfide. But more of this is going to be released at higher pHs. So at higher pHs, your eggs are going to have more of this egg flavor. And also more is released with higher temperature or longer cooking. Some of you may have seen this in the custard lab. If you notice that the custard that was cooked not in a water bath, that experienced higher temperatures, if you notice that that had more eggy flavor than the control custard. It's not a surprise if it does, because cooking at that little extra high temperature would have released more of this hydrogen sulfide and would have given it more of an eggy flavor.